Assalamualaikum everyone, salam sejahtera. So for this topic, we will learn on immunological memory. So what is immunological memory? Immunological memory is actually related to the immune cell, the memory cells that have been produced earlier in the adaptive immune response. So as we can observe here, this is an immune cell that recognize the antigen or the invading pathogen for the second time. So this ability to recognize the previously encountered antigens, this ability possessed by our adaptive immune response, which in the form of memory B cells and also memory T cells. So these memory cells will give advantage to our immune system to respond faster for the second time or the third, fourth time when the same antigen, same type of antigen try to invade our body again. So let's have a look. I mean, we will refresh back. We already learned about this mechanism before in the I think the second lecture. The mechanism of immunological memory. We are talking about activation of the third line of defense or adaptive immunity. So this where the invading pathogen being engulfed by phagocytosis process by our phagocytes, and then phagocyte, of course, phagocytes is a type of antigen presenting cell. So as their name, antigen presenting, so they will present the antigen to the helper T cells. Now once they meet, this will activate the naive T cell, that means inactive dormant T cell to become active or effector cell, effector T cell. So this active helper T cell will produce interleukins, type of cytokines. So this interleukin cytokines will act as a messenger to stimulate here the B cells to produce antibody or the killer T cells. So immunity is a evolve the memory cells, which this is the type of cell that provide immunity. So the advantage to us, we can have a faster response to the same invader for the second time. So this actually, how can we know? How can we observe all this? I mean, we say that yes, adaptive. They have memory cells. They will produce antibody in second time. So actually, how can we observe this in the labs? So we can observe this by observing their antibody levels or titer in the serum or plasma of the patient's blood. So here is the level of antibody titer. So how many antibody, and this is for the length of time. And I mean the time that needed to for the primary response or secondary response to become activated. So we look here on the day 0. I mean the first day or where you are being exposed to the antigen. Let's say people or patient, this is the first day that they are exposed to SARS-CoV-2 or COVID-19 virus. So maybe they contacted their relative or family members, or maybe they went to the mall, or they exposed to the virus. So we can observe a lag period or lag phase. So this lag phase actually where the body does not produce any antibody yet, because this is the time we know that we have innate immunity So in innate immunity, we have phagocytes that need to engulf the antigen, or any other immune mechanism, such as natural killer cells to destroy the virus infected cell, and this will lead to the process of bridge between innate, where antigen presenting cells present that particular antigen to the adaptive immune component, to the T helper cells. So all the process that we have learned will start, we begin production of antibodies by the plasma cell. So slowly we'll go to the log phase. So log phase is the exponential phase where the antibody level will start to rise. So we can imagine this is where the plasma cell, the B cell, the activated B cells will divide themselves to a large numbers, and then all those plasma cells will be very active and start producing a huge volume of antibodies, and then release it to the whole body, especially into the blood. So log phase is where you can observe by time frame, day by day, the antibody level will start to climb. And then it will come to a period where the antibody level will be in a state of plateau phase. I mean, they will become stationary. There is no more increase. They are producing antibodies. That means the plasma cells are responding well, producing a lot of antibodies. But in the same time, the antibodies will already destroy a huge number of invader, the antigen. So they are fighting here. The antibody is destroying the antigen, all the T killer cells, all the activated immune cells, and then we can observe a decline in the volume of antibody, because this the part where we can say that our immune system already won the battle. They defeated the invader. So they will have signal that yes, the plasma cell, no, you guys don't need to produce any more antibodies. So they will stop. They will some of the plasma cell will become memory cell. Some of T cell also will become memory cell. They will be stay as a memory cell, stay dormant, and the rest of the activated cell will begin to degenerate. They will start to die off. So we can observe a decline in the antibody. So we also can observe actually our body is normal body response to infection. Our body will produce the two main type of antibodies. First is IgM. So IgM is the first antibody that will be produced to any form of any response to pathogens. So IgM will be produced. In the meantime, the body also begin to replace the IgM with IgG. That means the plasma cell, they will start to replace the IgM with IgG. So we can observe that once the IgM reach their peak, the IgG also begin to rise, have their own log phase. So now this stage we have both IgG and IgM in our system. Both are attacking the same pathogen. So, but we know that IgM, they are in a form of pentamer, so they have a bit different way. They are more pro in agglutination. So IgG is the smallest antibody. They can go everywhere. So both of them work together, fighting the same pathogen or antigen. And also around 2 weeks. So this normal. I believe you guys notice this, that every time that you have a flu or fever, around 2 weeks, you will be better already. I mean, actually not 2 weeks. Usually around 1 week, 2 or 3 days or more. 2 weeks you already fully recovered. And then we can observe here the IgM level will start to decline almost to the level of very low. Also the IgG, so they will stay that way. This is the primary response. I mean, the first exposure, the first time the body being exposed to the antigen. If we talking about COVID-19, so this is the first time that particular person or patient exposed to COVID-19 in his or her body. So he was recovered. Somehow, so this is like the secondary response. It's not necessary to happen. This is just to show how our body respond if somehow the patient being exposed for second time. Okay, primary, yes, COVID-19 exposure the first time, recovered. But the second exposure is not necessary, but we want to show here how fast and how exponential, how much different between the primary response, the first response, to the secondary response. So we can observe here the lag phase is very short compared to the lag phase for primary response. Very short. And then the level increase is somehow quicker than the log phase for the primary response. The log phase for secondary response is quicker, and especially for the IgG, they will produce a lot more antibodies, much higher in volume, the antibody titer, compared to the first exposure. So this is the evidence that our body already have some sort of memory. They remember that antigen. So that's why our adaptive immune system, since we already have the memory cells, we don't need to went through the same thing. I mean, we can skip the antigen presenting cells part, the activation of the helper cell part. We can skip that. The memory cell, the memory B cell, they will just simply become activated and produce antibody. It's that simple. I mean, why they are faster and quicker? Because we already have memory cells in action here compared to the first exposure. Okay, so remember that memory cell. What is the benefit of memory cell? So we can say that because we already have memory to that particular thing, so it is an advantage, so that you can learn from the first time, the first exposure. The memory B cell is already there for the same antigen. The memory T cell also already there for the same antigen. Okay, we can talk a bit here. First, I want to stress on the lag phase here. Okay, lag phase or seroconversion phase. If we apply in the hospital, okay, this is the phase where, let's say, I am talking about COVID-19 patient exposed to COVID-19. that particular person already have COVID-19, already being infected with COVID-19 in their body, but because they are just exposed a few days, the body is yet to produce antibodies. And if you guys Google, try to look what are the tests to detect either how people is being infected with COVID-19 or other disease, other infectious disease. Try to look, try to Google it. There are two types of tests. First, the cheapest one, they will do serology test or ELISA test. ELISA is the method. So they will try to look for the antibody produced. But the problem is, if they went to the hospital before their body already produced the antibody, so they will be regarded as negative, even though they already have COVID-19 in their body. So in the practice, this why the patient need to wait for, I'm not sure now, maybe 10 or 14 days. You need to confirm, you need to look on the newspaper, our government protocols. So I believe before 14 days, that particular suspected COVID-19 infected person we need to go for a second round of test, diagnostic test. So this we are talking about the serological test. But of course we have another test which is looking on the antigen itself using PCR. So that one is much more sensitive. So PCR looking for the virus itself, not for the antibody for the virus. We don't need to wait for this lag phase to happen. But the PCR method is much expensive compared to the serological method. So this is the way. This is the usually issue in the hospital, because doctor want to see whether you guys have COVID-19, you get that patient have maybe HIV. So we don't know whether that particular person or blood donor, okay, in the case of blood donation. So this is very dangerous, the lag phase, because maybe the particular person donate his blood or her blood before the antibody begin to be produced. Okay, now we look on the types of immunity. So this immunity, we are talking about immunological memory. So how do we develop this immunity? So for immunity, we have two types we already learned. We have innate immunity. Innate immunity doesn't have any memory on it. They are not specific, and they do not develop any memory cells or memory to that particular pathogen. But for adaptive, we do. Our body, that means our immune system, do develop memory to it in adaptive immunity in the form of memory cells. So how our immunity can develop this adaptive immunity or immunological memory? There are two ways. First is natural. Second is artificial. I mean, this you don't need to do anything, or you don't need to consume anything or go for vaccination. Become will naturally or artificially, we can stimulate the body to produce, to have the immunity to that particular pathogen. For natural, we have passive and active. I mean, they happen naturally, and we have passive. Passive, we can observe between pregnant mother or mother with her child, so maternal, while the baby inside the womb, or lactating baby, I mean breastfeeding. Or active through infection. So everybody will go through this natural. This, I believe, this when we were born, we have this. Even when our mother is carrying us in her womb, we already being protected by the IgG from mother, and then while we have our breastfeeding period, our mother will share his IgA. I mean, IgA can IgA is available in the body secretion, including breast milk. So we are protected by natural passive immunity from our mother, or active everyday through infection. So when we have fever, we have flu, so we are protected by active infection. So artificially, either by passive, the same passive or active. Passive mean antibody transfer. So this seldom being done, not very popular, but also being talked earlier. I think between April or May, quite a hot topic. People are talking about, can we transfer antibody from COVID-19? I mean, people that are already have COVID-19 but they heal from it, they doesn't suffer from COVID-19, so they have a very strong antibody. The doctors around the world is looking at trying to transfer antibody from those people. That means COVID-19 antibody already produced from another person to patient that are suffering from COVID-19. So this method is not exclusive to COVID-19. That means being practiced on so many infectious disease, and also active by immunization or vaccination. So we now very hot, also very hot topic now, every day in the newspaper. We have as for our country, we have I believe two candidate for vaccine. One from China, and one is from I think from the Europe, producing a vaccine for COVID-19. So again, we have a look again on the four basic types of immunity. We have active and passive. If we try to look on the passive and active type, this picture showing natural and artificial. So I try to present it in quite a bit different way from this picture. So okay, active immunity, if naturally acquired through immune response, the activation of B cell or T cell upon exposure to antigens, resulting in production of memory cells. So what we have already learned in the adaptive immune response. Or artificially acquired through vaccination. That means we voluntarily introduce antigen to our body, so we can develop immunity to that disease. Okay, antigen that have been pre-treated. I mean, of course, in the case of again, I'm still talking about COVID-19, so you guys have more interest on it. We are not going to inject a live active COVID-19 virus, so they need to be changed, treated, killed or whatever, to make sure that they are harmless, but they still able to produce immune response, immunogenic but not pathogenic, not producing any disease introduced into the body, so we can develop immunity to it. Okay. As for passive immunity, for naturally acquired, the transfer of IgG antibodies from mother, from pregnant mother to her baby. So every day the mother sharing his IgG to protect the baby. Even when after the baby is born, from mother to baby, again in the form of breastfeeding. I mean IgA being transferred to the baby. Artificially acquired, where we inject antibodies into the patient. I mean, we try to inject because maybe the patient cannot produce or not yet able to produce enough antibody to fight that particular pathogen. So we help the patient by injecting antibodies from other sources, such as from another human or maybe another from animals.